All right, speeds and feeds. All of those magic numbers come from somewhere. They don't just Mastercam produces them. We go through our values. You go into the machinery's handbook and you look up and you calculate it out to the point zero decimal, and then the machine rounds it off to 1 RPM or off to 1 inch per minute anyway, or point uh, 2 decimals on the inch per minute. So you can calculate it to whatever precision. The machine's going to have its variation, and you really comes down to one of my favorite sayings: observe and react. We're getting it closer. Can I speed it up? Can I slow it down? Right? There's no, it has to be this way. Right? Now on the TM, we have 4,000 RPM spindle. I run it at 4,000 RPM and 12 to 18 inches a minute because the rigidity of the machine, that's what it'll handle. VFO, 10,000 RPM, and that same half-inch tool is 9,000 RPM between 40 and 50 inches a minute. It's still not at its peak performance, but I'm a little afraid. Okay, I'm a lot afraid. All right, something goes wrong, it goes wrong very fast, and then you don't have a chance to correct for it. So you have to be within your comfort zone of what you can respond to. And after I've run the program, like I said in the earlier lecture, is if we're making 10 parts, I really don't care. I just got to get them done. At 100 parts, I'm a little more concerned, and especially if the cycle times are up, enough to where I can save a significant amount of time making these minor adjustments. But as soon as we go to thousands of parts, I want every second. I want every of tool life and of cycle time. So speeds and feeds is based on the standard formula, 12 times, so 12 inches per minute times the cutting speed. Cutting speed were determined by experimental values, so people destroyed a lot of tools to come up with those values. All right, so recommended values in the machinery's handbook, you're going to find the block of steels very close together. The aluminums pretty close together. What it's not telling you is the ductility of, for example, in the aluminums, the 5052 and the 6061 are very similar in cutting speeds and feeds, but the 5052 is a little gummier. It's going to try and weld up if you don't keep the coolant flowing to it. If you get it a little hot, it's going to go away a lot faster than 6061. It doesn't have the same shear. It wants to flow. Those are our basic properties and materials that feed into this that we're having to account for. All right, so the 12 inches per for the to go to the cutting speed, and then pi times the diameter is our circumference. So basically 1 point coming around on that cylinder, coming around on that end mill, is how many surface feet per minute we're dealing with. So to have the same value, if we said 100 surface feet per minute for a 1-inch tool, that 1-inch tool is going to run a lot slower than an 1/8-inch tool to maintain the same amount of surface feet per minute. So when we do the calculations, we'll see that an 1/8-inch tool probably wants to run at 12 or 15,000 RPM or 30,000 RPM depending on the conditions, where that 1-inch tool is probably going to stay in the, I can run it at 2,000 or 2,500, something like that. All right, so just running through, and then it reduces to approximately 4 times the cutting speed divided by D. All right, so if I take pi and divide it into 12, I get close to 4. It puts it a little on the high side, but that's math I can do in my head. All right, so if I see something that's out of, wow, that's a little on the high side, or it's out of line, I should fall back on these to make those values. So the other one then is I went back, and every time I do anything related to metric, I have to look at my formula. So it's 1,000 millimeters per minute. Did I reverse that again? Yeah, I think I did. So then you go to surface meters per minute divided by pi times the diameter in millimeters. And that's going to return a value 318 times V, or what would be our cutting speed still, and divided by D in millimeters. All right, so it looks like a weird number. You should be able to put that in the same context that the programs that I've run in millimeters or generated in millimeters. If it's at 500 millimeters or half a meter per minute, then that corresponds to about 20 inches per minute. So you kind of do that quick translation, 40 inches for 1,000 millimeters or 1 meter. All right, so it depends on how the machine I didn't walk out to the machines to go, yeah, is it actually, you know, in millimeters or in meters? So at the if you go out to the Haas tip of the day, they actually have speeds and feeds for inch and metric. If you haven't signed up to receive the emails for the Haas tip of the day, it's kind of interesting. They have a lot of good recommendations. Their speeds and feeds, instead of the 4, I think it works out to 3.85 something something, and it's at that point, let's just round it. It looks cool though. All right, so I jump over to, this is the general sheet that I've used forever. Same formula, RPM equals 4 times the cutting speed divided by D, where the tool is D for milling and drilling, and the stock is D for turning. So when we go over onto a lathe or we're on a turning center, we're starting off with stock at 1 inch, and that has that same value because the tools are stationary doing the cutting. The general rule is carbide is going to be 3 to 5 times that of high-speed steel, so we calculate for high-speed steel and then multiply it out. Right, so I'm always going to be a little more aggressive. I have that increased rigidity, the chip ability to eject the chip, and to take advantage of that that increased cutting rate, cutting RPMs. Yeah.
So are speeds and feeds going to have a lot of effect on your tolerances?
Can. Yeah, if you are too aggressive, then you're injecting a lot of heat into the material. The tolerances will grow and shrink accordingly. Is the coolant being effective, or on the one machine that I run is kind of an open body, so I end up using a cold air gun, and it can cool at the tip, but then it also is, the part is kind of cooling and going through that thermal cycle. I do see a little bit of shift. So, you know, the question is, are you holding plus or minus 5, plus or minus 5/10, plus or minus 50 millionths? And then when you get into that 50 millionths, tenths, to 5/10 range, you look at it wrong and you breathe on it, it changed tolerance. So, it's one of those conditions of the shop, as well as all of these other conditions play a factor in it. So for the most part, if you are roughing, you're roughing it oversized so that you can remove that material very quickly. And then when you go to the finishing, that's bringing it to size. That's what's holding your tolerancing. And you're reducing and giving the tool a chance to cool, stabilize, material to cool and stabilize. So the general categories, the super alloys can be between 10 and 50 surface feet per minute. You're not going to run high-speed steel in titanium. Well, you're not going to run it very fast anyway, or for very long. You get into the Monels, Inconels, the high nickel content, chromiums, any of the materials. Slower is better. Speed is not your friend. Right? And then we're going to go start looking at, then again, coatings and additional things that we can do to the tooling to increase its life expectancy in the material. So a lot of the titaniums depend on grades. Grade 2 through about grade 5 is not that much more difficult than stainless. It's just as soon as the tool starts to break down, it's not sharp anymore, the tool's going to break. Same with taps, is they have to stay sharp. They have to be right there. Stainless is more forgiving. It will even, you still have to be careful of the work hardening and the other properties that come with the stainless. But as the tool breaks down, you're not going to see that immediate tools broke from it getting kind of dull. Tool steels, so like the O series, D series, S series, H series tool steels in that 30 to 60 range. Again, from the Machinery's Handbook, if we had a specific grade of steel, then we would go back and look for it. The general hot rolled and cold rolled 1018s, 1020s will be right there at 100 surface feet per minute. The hard bronze and those get into that same grouping at 100. And again, if it is an oil impregnated bearing bronze, then you want to keep the heat away from it because the oil is going to migrate away from that tool tip and migrate away from the cutting. We probably won't put a lot of coolant on it because the coolant's going to displace the oil in the bearing material. So again, a lot of considerations when you're looking at this material and understanding the properties of the material that's been selected. Plastics would say 100 to 300 if you're dealing with a Rulon, any of the glass-filled resins. We're going to be carbide and we're going to be slower, and it's going to be really abrasive, and it's going to go through tools. But you go up to something like Teflon, then we can run a little faster, but Teflon's another one of those fun that you look at it, it's going to move. And you get a little heat into it, it's going to move. And holding tolerances is next to impossible. Right? If you have a really soft PTFE Teflon, it is going to require really just a lot of effort to hold the plus or minus 5 because it is so soft and it's machining bubble gum. All right, so the plastics have those range. Everybody is, at least my favorite, Delrin, the acetyls, very stable, hold the temperatures, and are going to hold good tolerances over a wide range. They also absorb the moisture in the coolant, so it will swell, and when you let it dry out, you will see a tolerance change as it shrinks. All right, not a lot, but if it's a tight tolerance piece, it can be enough. And then our aluminum favorite, 6061 is about 200 surface feet per minute. And I can do that math of 4 times 200 is 800 divided by the diameter. Even if I have to get out my phone and type that in, it's 800 divided by whatever, and then multiply it 3 to 5 times based on the tooling. So at that point, we go back over to the coatings. And if it's tin coated, if it has aluminum, the Altin, aluminum titanium nitride, if it's, I can go down the list of coatings, those are all going to have an effect on lubricity, on tool wear, on the cutting edge holding up. Last was the brass, bronze, and copper. Again, copper is machining bubble gum. You're going to have that heat is not your friend. The heat wants to transfer, dissipate through the material. So as it grows, as it shrinks, then you're also having to worry about those chips flowing up into the flutes, welding up, and pretty much stopping the cutting action. Right, so 200 to 300, and then brass, bronze, and coppers. Electro-grade copper was a lot of fun, but don't recommend it a lot. All right, so the inches per minute then is RPM times the number of teeth times the chip load per tooth. Roughing is 2 to 15 thousandths. Again, stopping on the low side, about 2 to 5 thousandths is where I will keep a really aggressive roughing pass. Again, depending on the rigidity of the machine, what it can take as far as the movement. The finishing, 1/thou to 5 thousandths. Really, we end up with numbers well under 1/thou. Anywhere from a couple of tenths per flute, all the way up to about 5 thousandths. So it's not a set; it's more of a range. And again, observing and reacting. What is the finish looking like? When I do the calculations for some of the examples down here, they don't make sense, but the observation is, wow, I can get a mirror finish if I drop the RPM, increase the feed rate, and let that tool load, feeding into that last little bit of finish cut. Our rule for reaming, half the speed, twice the feed. So we do the calculation. Most of our reamers are going to be high-speed steel, unless we specifically purchase carbide. So we do that calculation. It comes out for a 1/4 inch. I think it's a 1/4 inch tool, and the steel was at 3200. So we would run it at 1600 RPM, and our inches per minute was 10 or 12. We'd run it up to 24. All right. So whatever our resulting values, we divide the 1 in half, multiply the other by 2. And then from the Machinery's Handbook, life of the cutting tool most affected by cutting speed. Too fast, you're putting a lot of heat into it, looking for those brassy kind of purplish chips. As soon as it goes over to dark purple and into the black, that's probably a bad thing. You're starting to burn up the tools. Feed rate, getting it loaded, Comes back to the rigidity of the tool, the holder, the machine. And if you're getting a lot of tool deflection, that's going to put a lot of internal loads, a lot of internal stresses on those tools. And then the depth of cut. Depth of cut is still one of those factors that, yeah, it's least of all, but if I have a high feed rate with a heavy depth of cut and I can't get the chip to evacuate, I can't get it to clear, I can't really trust that depth of cut. So we've got to either go to the trochoidal cuts where we're reducing the axial or the radial engagement so we can increase the axial engagement. And that's the value of those little nibble cuts, is that I can go into a very hard steel, into the titaniums, into the alloys, and because it's only removing 5 or 10 thousandths, but we're at an elevated feed rate, I'm removing that much more material, but the heat's being carried away with those smaller chips. And we're using more of the fluid of the end mill so that we can get better life expectancy. Most of the end mills, we cut that quarter-inch step. So if you look at a tin coated after 100 parts or so, the tin coating is going to be wore off at a quarter of an inch, and that's going to indicate that there's going to be a little bit of taper. Right? As we run that tool more and more, it goes from a finishing tool to more to a roughing tool. All right, so feeds and speeds it's kind of is you start with your best guess. You pick the mid range, and then you build out from there, seeing what the tool can handle. All right, so I didn't have a really good place to do threads, but threads tie into the feeds and speeds. So my favorite formula is for the machine threads is the number times 13 plus 60. So instead of carrying around a machinery's handbook that tells you the major and minor diameters of all of the machine thread forms, I start off with the number 10. 10 times 13 plus 60 is 190. If you want to think of it as dividing by 1,000th or just plop a decimal point in front of it, 190 thousandths is the major diameter of a number 10 machine screw. And then the pitch, the second number, the dash 32, 1 divided by 32, the 0.031. The major subtracting the minor gives us 159. That is our tap drill. All right, so for the machine screws, not so difficult to come up with those values just off of the fly. The fractional is pretty much the same thing, except we're just doing the decimal conversion. Quarter inch goes over to 250. 1 divided by 20 for the pitch, 50 thousandths. 250 minus the 0.05 gives us 200 for the tap drill. We go to the index, there isn't a 200, it goes 199 or 201. That's why you get a number 7 201 drill. And then in metric, I always say that in grade school we were taught 25.4 millimeters to an inch. I can never visualize 25.4 anything. But if you tell me about 40 thousandths, I'm right there. I got that as a visual. So my number is 39.37000 and a 5 or 2 out there, way out there, inches in a meter. And if I divide that by 1,000, then I get 0.03937 millimeters, and that rounds up to about 40 thousandths. My advantage to 40 thousandths is that most anybody can multiply by 4. So if I tell you a 6 millimeter, 6 millimeter anything, 6 millimeter tap, then 6 times 4 is 24. Throw a 0 on the end of it, you got 240. Actual is 235, 5 something, 236, call it. We're within 5 thousandths of our nominal tap conversion or millimeter conversion. So a number 8, 32. We go to 320, actual is 315. We're still within 5 thousandths. So I can get that number very quickly and get it into my conscious visual that it's either a really small or a really big number. And once I get to the 320, it's not that big of a deal to get that trigger to go right into 315. All right, so we get to the reciprocals, 1 divided by 0.037, 25.40005 inches. And if you get out that far and you are making flight-ready instruments, all of a sudden that 0005 is a little more important, right? Especially as we get further away and higher numbers. And then, there's the 4. And then, of course, the metric taps are so complicated. You take the major diameter is the M, and the pitch is the second number, and you subtract the first number, or the second number from the first number. That gives you the minor diameter. So, our example, an M6 by 1, 6 millimeters minus 1 is 5 millimeters. And because we can multiply by 4, I'm going from about 240 to about 200. 197 if we actually do the math. All right, so it's not, I can always get out the calculator and verify, but in the process of design or in the process of programming, I want to key in on it visually and mentally right then and there that my numbers make sense, my speeds and feeds make sense, whatever we're telling it to do for threading, those all make sense and we're getting good values out of it. I think the next one goes into the MOT. So we've done work holding, we've done tooling at RPM, probably should be feeds and speeds. And the real question is, when we sit down and we look at all of those basic decisions that we made up to that point, somebody had to order material. So what kind, size, and condition? Is it plate? Is it bar stock? Is it oversized? Is it right on size? Am I going to have to manipulate it to get it to be really close? So that falls into the envelope, and also the envelope of the machines. Are we running on a really tight, just within the vise, or can I put up multiple vices because we're going into production? Are you from the Mastercam programming side? CAD drawings or models. If I'm working off of a piece of paper and I have to reproduce it, then I'm typing those things in. So just like we're doing on the first couple of assignments here, we're creating that geometry within Mastercam or within our CAM program. Or do I take it over into a SolidWorks, into a Fusion, into an Inventor, Onshape, go down the list, and output it to something that we can use as a model. We've asked the question a couple of times, how many? 1, 10, 100, 1,000? At some point, it's going to drive decisions. I jumped around here a little bit. So our available equipment, available personnel. Do you have personnel with the technical experience to hold plus or minus half a thou? Hold plus or minus a couple tenths. Will it be able to massage it in? Cost of operation for machine. If I can do this hole on a drill press and it costs me 10 cents per hole to pop that hole through, or do I take it over to the wire EDM and EDM it to plus or minus 50 thousandths, or the jig bore machine plus or minus 50 millionths, and all of a sudden it's a $10 per hole cost. Well, it's not a very effective use of our cost of operation for the equipment. And then back to the rigidity, will it take the types of cuts that we're doing? So work holding, fixturing, and then the tooling, carbide, high-speed steel, and the feeds and speeds that we're going to be able to run. So the question is, how do we get from the print to something that's in production and making finished usable parts? Slip one more. All right, so then next time we'll talk a little bit more about axes and setting up the machine.